So if you think that last mini lecture ended a little abruptly, it did because I lost track of time. So we're going to wrap this all up, the spin-spin splitting topic, with some important caveats and examples. So the important stuff, the details are in your textbook, but I'm going to hit the highlights. The most important one is that n+1 really 90% of the time applies to just those next door neighbors, and that's called the vicinal coupling that we've been looking at examples of already. One really weird aspect is that if you have chemical shift equivalent nuclei right next door to one another, they don't couple. So for this molecule, 1,2-dichloroethane, you'd look at it and you'd say, well, gee whiz, these hydrogens are obviously next door to 2, therefore I would fully expect this to be a triplet and this to be a triplet. But it's not the case because all 4 of those are identical, and therefore the proton NMR spectrum for 1,2-dichloroethane shows up as a nice clean singlet. Same sort of example for benzene, 6 hydrogens. They're right next door to one another, but there's no coupling, another perfectly clean singlet. Now, a pet peeve of mine that is not stressed in many textbooks is that when we're talking about the n+1 rule, what we're really talking about are homotopic nuclei, chemical shift equivalent nuclei. So if I were looking, for example, at this particular molecule and trying to predict the pattern for the orange circled hydrogen, well, by the n+1 rule, I'm not sure what I'd do, because these guys are H sub A and these guys are H sub B. These hydrogens and these hydrogens are not chemical shift equivalent. These will show up in one place on the spectrum, these in another. So what that means is I cannot just do n+1 and say, well, there's 4 neighbors. This should show up as a 5-line signal because they're not chemical shift equivalent. The way we get around this is by using something called tree diagrams, and that's a little bit more complicated, and we'll talk about that a little later on. I will say that it turns out that the orange circled hydrogen does show up as a 5-line signal, but that's just a lucky thing, okay? We really need to understand it by drawing tree diagrams. So when we say n+1, we're talking about homotopic hydrogens. In this particular case, what ends up happening is that the orange hydrogen is split into a triplet by H sub A, and then that triplet is then split again into another triplet by H sub B. Since they overlap, it looks like 5 hydrogens. Now, the book covers exchangeable hydrogens in good detail. I just want to point it out, as an important caveat, that even though these 2 are neighbors, and you might look at this and think, well, the methyl is going to be a doublet and the hydroxy is going to be a quartet. It's 2 singlets because that hydrogen is rapidly exchanging with other molecules of methanol in the NMR tube or beaker or whatever. So that hydrogen is not bonded to the oxygen long enough and strong enough for those 2 neighbors to actually talk to each other and couple. So exchangeable hydrogens, no coupling. Okay, the n+1 rule is a rock, an absolute rock. So if I have a molecule that I'm looking at the NMR spectrum and I'm thinking, well, I think that there's probably that substituent in there. This has no neighbors. This absolutely, positively must show up as a singlet, and there are no exceptions. Period, the end. So if your spectrum doesn't have a singlet, you don't have this methoxy group in there. You know, there's a little fudging with chemical shift. We've seen that because of the ranges in the correlation charts. But N+1, no fudging. Unless, well, the thing with N+1 is it only works, it's only obeyed, and you get nice clean doublets and triplets and quartets, etc., when the difference in the chemical shifts between the two signals is much larger than the coupling constant. When this is true, what you have is called first order spectra, and N+1 is obeyed. So the easy to understand translation is, you want to see N+1 spectra, the chemical shifts of your hydrogens have to be really quite widely separated. So for example, methyl cyclopropane, we might look at this structure and think, well, I should see some pretty nice, easy to interpret patterns here. I know, for example, that these 4 hydrogens would be chemical shift equivalent. And while I know they're not going to couple each other, they should be split into a triplet by the adjacent CH2, the adjacent methylenes. Well, you can look over here, and you sure aren't going to find a triplet. In fact, all you're going to find is a mess, because the chemical shifts for all of these signals are too close to one another that that relationship does not hold. The difference in chemical shifts is not much larger than the coupling constants, and so N+1 does not hold. You cannot dig any kind of useful coupling constant or neighboring hydrogen information out of this, because there's no first order spectra here. Alright, so we're going to wrap up with a few examples, and we'll do a lot more of this in class, but let's just quickly try and reinforce everything by predicting the expected proton NMR spectra for some examples. Alright, ethyl methyl ether. Number of neighboring hydrogens here. Will I go over to one atom? Are there any hydrogens here? No. So that would be a singlet. Here's my carbon. How many neighbors does this set of hydrogens have? Well, I go over here. No hydrogens on this neighbor. Go over here. 3. Therefore, this should show up as a quartet. How about the methyl group? Go over one atom. How many hydrogens are on this atom? 2. 2 plus 1 is 3. This should show up as a triplet. That is bells and whistles. A quartet and a triplet is bells and whistles for the ethyl group. So if I see a quartet and a triplet with the same coupling constant, we're talking an ethyl group. Alright, how about this diisopropyl benzene? First thing I'm going to do is get rid of the stupid line structure and put in my hydrogen so I know what I'm really looking at. So now I see I've got 3 sets of hydrogens. H sub A, H sub B, and H sub C. Very symmetrical molecule. So I would expect to see 12 methyl hydrogens down around 1 part per million, 2 methine hydrogens pulled downfield by the aromatic ring, plus the fact that they're methynes, this might be around 2.5 or so. And then, of course, the aromatic hydrogens, somewhere in the range of 7 to 8 parts per million. But what patterns would we expect? Well, for these methyl hydrogens, how many neighbors do they have? Well, on each side, they have one neighbor. So they would be split into a nice 1-to-1 doublet worth 12 hydrogens. Well, how about the methynes? Well, gee whiz, the methynes have 6 neighbors. So 6 plus 1 means we're talking about a 7-line signal. And those are kind of hard to draw and see, especially when you consider that this is one lousy hydrogen. So in the actual NMR spectrum, you might not even see all 7 signals. You might just see pretty much the inner 4 or 5, because it's so small it'll be buried a little bit in the baseline. So for this particular example, I would expect to see a doublet around 1 part per million. That wouldn't be 1 hydrogen, it's 2 hydrogens because we've got a symmetric molecule. A septet worth the 2 methine hydrogens down around 2.5 or so. And then all the way down to 7 to 8, a nice 4 hydrogen singlet for the aromatics. All right, one more example. No, I think I've got 2 more examples. How many different chemical shift equivalent hydrogens do we have? A, B, and then all 9 of these are the same because we've got free rotation about that carbon-carbon bond. They're absolutely in the same identical chemical shift. They're chemical shift equivalent. They're in the exact same electronic environment. All right, neighbors. Well, looks to me that for these 9 hydrogens, if I go 1 carbon over, there's no hydrogens on that carbon. Therefore, these should show up as a nice singlet. Again, probably around 1 part per million because there's nothing particularly shielding or deshielding about their environment. Okay, how many neighbors for this guy? Well, over here, no neighbors. Over here, 2. Triplet. How about here? Obviously no hydrogens. 2. Triplet. What should I see? This should be around 2.3. I'm never too good with the halides. I'd have to use the correlation chart, but I'm going to guess this is around 3. Don't quote me on that. So what would the spectrum look like? 1, 2, 3. So around 1 we got a humongous singlet worth 9 hydrogen. We got a little triplet. 1, 2, 3 worth 2 hydrogens here at 2.3, and then around 3 or so another triplet. You know, I'm not going to give up my day job, which shouldn't include drawing NMR spectra, but that's what I would predict the proton spectrum to look like. And last example, again, a pretty symmetric one. So we have 4 there and 2 here. Now here is an example where another example where I can absolutely add these guys up because they're all 4 chemical shift equivalent. So this would be 4 plus 1. So this would be a quintet, a legitimate quintet, and these guys would be a triplet. So those are some great examples. Start thinking. We've just looked at these from one direction. what we're going to need to do in class is look at a spectrum, look at the patterns, and say, given this spectrum, let's say we're going to have a little something like that, what structural features can I infer from these chemical shifts, integrations, patterns, and coupling constants? In other words, we need to go both ways. Look at structures and predict spectra, predict structures. No, excuse me. Look at structures and predict spectra, and look at spectra and predict structures. Okay, enough is enough. We will see you in class.